Hi, my name is Carlos Rivera. I'm the Global Product Specialist of FEFLOW in DHI, and today in this on-demand webinar, I would like to demonstrate the use of hydromechanical processes in FEFLOW with our new release FEFLOW 7.4. The agenda for today's webinar is an introduction about hydromechanical coupling methods in FEFLOW. We will go through all these methods for different porous media, fractural and granular media, check the different representations in the software, understand what are the set of parameters that you require to get started with this. And in the second part of the webinar, I will give you a live demonstration about the usability of this plugin. Motivations. Before we start with the motivations, we need to define few parameters. Effective stresses. Effective stress describe the stress state of a saturated rock and results from two parameters: load of principal stresses or lithostatical stresses or total stresses. This is described in the equation as sigma in red color, and pore pressure. Pore pressure being a parameter calculated in FEFLOW all the time. In FEFLOW, this parameter is mentioned pressure and is found in the data panel in the software graphical user interface. Pressure in FEFLOW is a secondary parameter because firstly, we simulate and calculate hydraulic head. Pressure is derived from the information of hydraulic head. Changes of effective stresses induce changes in the intrinsic hydrodynamic parameters. In concrete, effective stresses are going to modify conductivity of the porous media, porosity, and storage coefficient. An increase of effective stresses is basically driven by a decrease of the pore pressure. This decrease of pore pressure could be due to pumping, due to dewatering in a mining application, dewatering in a geotechnical applications like tunnels of civil engineer construction, etc. Let's take a look at typical cases where effective stresses are relevant. What you see in my screen is a very famous case in USA, the case of land subsidence in California. Specifically speaking, is the area of San Joaquin Valley in California, which records significant changes of the topography, so land subsidence over the last years. Another example is Mexico City Basin. Here also, since 20-30 years, is being observed a problem of land subsidence due to the overexploitation of groundwater resources in the Mexico City Basin aquifer. Another typical case where this hydromechanical process will be applied is to evaluate the well production. There will be a reduction of the productivity due to the compactation induced by these changes. So we start compacting, consolidating the material, so we will decrease the conductivity, close the porosity, and therefore minimize the well productivity. It's typically the case to look effective stresses and consolidation effects in the case of drilling of tunnels. You will be typically interested to analyze the effect of stresses in the area surrounded by the tunnel. There will be a dewatering process associated to the tunnel excavation. There might be a case of infiltration into the tunnel. This will change significantly pore pressure. Therefore, we need to look for effective stresses and consolidation effects associated to this. The other typical case is mining applications, open pits, tailing facilities, and other type of engineering structures used into the context of mining. Ground at leaf recording areas of subject to fluid injection. This will be the opposite to the cases described previously. In this example, we will, for example, inject a significant amount of fluids. Could be the case of a geothermal energy projects, which could induce some hydraulic fracturing of the media. Changes of fracturing in the media will be induced by mechanical process, and we will obviously need to understand what is happening with the hydraulic properties of the reservoir. Other examples are brittle deformations and large-scale glacial retreats, permafrost melting. Hydromechanical coupling methods in FEFLOW. How is this being implemented in our software? Let's look some of the definitions and the hypotheses used here. The main hypothesis is that we look principal stresses mainly in the vertical direction. Secondly, we are working in the isotropic elastic compressibility range. This means that as soon as you impose a force in the material, this will create certain deformation. But if the force is released from the material will get back to the original shape. That is basically the law of elasticity. And for this, we are following the very famous Hooke's law of elasticity, which in few words is described by the equation here. Effective stresses, a function of pore pressure, equal to total stresses minus pore pressure, and there is empirical constant associated to the pore pressure. This concept is robust enough to allow the possibility to incorporate hydromechanical processes in granular media and in fractural media. In the case of fractural media, we can represent fractural media by equivalent porous media, elemental selections in FEFLOW, or we can have a specific individual fractures or faults represented by discrete feature elements. On top of that, we can include effects of overbonding on the ground surface, for example, glacial retreats, large contraction sites, accumulation of solids, for example, from a tailing facility, among others. Our approach, compared to other solutions in the market, is reliable and is more flexible because we account for multiple changes of hydraulic parameters. We account for changes of hydraulic conductivity, porosity, and storage coefficient. If you want to look more details about implementation, I will suggest you to look in these 3 different papers, which are the basis of our implementation in FEFLOW piHMC module. Otherwise, you can also get an overview of this mathematical background through the user manual of the plugin. This user manual and the plugin, they came together with the FEFLOW installation of this version 7.4. Let's look some of these definitions for the fractural media. In the case of the fractural media, we use the principle of superposition. This means that you are capable to define a material property like rock conductivity or rock storability, and on top of that, we calculate what is the effect of the fractural media adjusted by effective stresses and put this effect on the parameters, on the material properties that you already defined in the FEFLOW model. To be able to solve this, we require empirical model. This empirical model is exponential model. Is presented here in the upper left corner of my presentation. And this empirical model requires 3 parameters. One is the limit effective stresses for fracture closure. So this means what is the pressure or the stress required to close a fracture. You have information about the asperities of the fracture, and you have empirical coefficient M to define the probabilistic distribution of this fracture in the system. Knowing effective stresses, we can plug this information of effective stresses in a function of conductivity and storability. For the case of granular media, the system of equations is a bit more simple. We have a stress model. This stress model relates porosity and effective stresses. Again, you require a closure effective stress to reduce the porosity to a minimum limit. And this effective stress limit of closure of porosity is related to an elasticity module, ES, and a porosity value. Let's look the effects of effective stresses in porosity and hydraulic conductivity. If you look at the graph that I presented here, if you increase the effective stresses, you will have or you will produce a reduction of the porosity in the system. In the case of hydraulic conductivity, Increasing effective stresses will tend to exponential decrease of the hydraulic conductivity. Let's go back to the first definition. Effective stresses, increase of effective stresses basically means that we are reducing the pore pressure in the system. Reducing significant reductions of the pore pressure will modify the grains in the material and will tend to close the porosity and therefore also decrease the conductivity in the system. This law of elasticity is also valid for small strains. Knowing the values of effective stresses, we can plug this information in the very famous Kosenik-Karman equation to get the values of conductivity and specific storage. Each granular family defined in the system requires input parameters, and the main parameters are listed in this table: elasticity module, porosity, and limit effective stress for pore closure. Having this information, we are ready to solve the system of equation. This is a nonlinear system because we have a coupling between conductivity, effective stresses, storability, and also porosity. On top of that, if you want to add effects of overbonding, we plug the concept of noisel in 1D to add this information into the system. As a main input, you require the definition of total stresses. This is something very simple to calculate because it depends on rock density. Rock density information is available in many literature papers. Total stresses are defined by rock density multiplied by gravity multiplied by depth. This depth is a parameter in FEFLOW which can be used or connected via expression, like the one mentioned here. Implementation in a FEFLOW plugin. Hydromechanical coupling plugin is provided with any FEFLOW installation of the version 7.4. The plugin does not require a separate license. If you have a valid license for FEFLOW 7.4, you are ready to get started with this hydromechanical coupling in FEFLOW. The plugin comes with a simple to use graphical interface. Is the one that you see in my screen. It requires a couple of inputs, like the definition of the stress field. You remember, you're required to create a nodal distribution for describing the total stresses, and then simply you connect this nodal distribution to the box total stresses on the upper left corner of the plugin graphical interface. You need to have a set of elemental selections. These elemental selections are used to define granular media or fractural media. They are added here in the section called formations. If you have multiple FEFLOW models with the same definition of granular and fractural media, it's easy to export all these formations. This will create an XML file, and you can import the same definition in the next FEFLOW file. So you don't need to always restart one by one the definition of formations. If you have individual fractures represented as discrete feature elements, this can be also listed here. Each formation, either fracture, granular media, or faults, require a specific set of parameters. These parameters, or the number of parameters, is defined depending on the type of model that you choose. You are also not forced to have a fully domain being coupled for hydromechanical processes. You can just select the area of elements where these processes are relevant, and FEFLOW will only take this area for the coupling mechanisms. Obviously, the reduction of the selection will accelerate the calculations at the end. If you want to add effects of overbonding, there is a way to prescribe this information via FEFLOW time series. You have a section in the plugin called Surface Law Function IDs, where you can connect existing time series in the software. The time series has information of time and values in pressure. So it's just telling exactly the simulation time where the law is going to be placed. Let's do some live demonstration and see how this plugin works in real life. Hi, welcome to the part 2 of this tutorial. In this example, we have a simple mining model in FEFLOW. You can see it's a box model. In the box model inside there is the representation of open pit. For matter of simplicity and demonstration, we have fixed the hydraulic head on the left and the right side. The pit is simulated by a seepage phase boundary condition in FEFLOW, so there is a potential equal to the elevation. This means the pressure is atmospheric conditions and with a constraint of max flow rate constraint equal to 0 in FEFLOW. To look a bit the effects of hydromechanical processes driven by FEFLOW piHMC module, I have decided to prepare a very simple distribution of conductivity. So the entire model domain has a conductivity of 1 meter per day, and this is isotropic in the 3 directions of the conductivity tensor. We will run the simulation and evaluate what is the distribution of heads, flow rate at the area of the pit, and then compare this with the next model where we include hydromechanical processes. So we just need to press start to run the simulation. The system is steady state. Okay, the simulation is ready. We can look the results through the process variables hydraulic head, double click. We see the distribution of hydraulic head, nothing that we didn't expect, so we have a decrease of the hydraulic heads in the area of the pit. I have also prepared a cross-sectional view which can be used to basically understand the distribution of hydraulic head. So we have the white line is the position of the phreatic surface. We have a fixed head left and right, and there is a gradient in the direction of the pit. Very simple. Now let's start preparing this model for the hydromechanical coupling. I have reloaded the send FEM file before we press start. To get started with hydromechanical process in FEFLOW, we require a couple of things. As learned in the previous session, we need to define a distribution of total stresses. This is under the section User Data, right-click, Add Nodal Distribution. Let me name this parameter as total stress. Per definition, this parameter is empty, undefined. I would like to create some information here. For this, the easy to do is to operate with the expression editor in FEFLOW. We have current expression, double click, open the expression editor, and we are going to define the definition of the total stress. Let's assume we have the same material, the same rock, density of 2,200 kilograms per cubic meter, times gravity is 9.81 meters per square second, times a parameter which is the depth. This parameter is easily accessible to the auxiliary data. Nodal depth is in meters. Double click. Okay, so we can close this. And last but not least, we need a selection and we need to assign the expression to the domain. Now I have the distribution of total stresses. If you made the math behind the units, the resulting units is pascals. As a next step, I need to create 2 containers for defining changes of porosity. What will be an elemental distribution? Let's call this deformation. And I would like to define a second container. This time is a nodal distribution, and this will be called consolidation. So the consolidation is computed at the nodal base, and the deformation is a change of the porosity, and since porosity is elemental base parameter, the deformation will be also elemental base. These parameters are empty, these are results of the calculation. We just need to fulfill this information here, or connect these 2 parameters in the plugin graphical interface. If you have FEFLOW 7.4, during the installation comes FEFLOW piHMC, you will have the plugin listed in your plugins panel. If you don't see your plugins panel, the best way to visualize this is to go to the menu View, Panels, and the last one is called Plugins. So let's open these plugin panels. I will attach the plugin. There is one requirement to operate with this plugin. This requirement consists that we define the conductivity with anisotropy settings. Normally, you will see here conductivity Kx, Y, and Z. To activate the anisotropy settings in FEFLOW, you need to go to the menu Edit, Problem Settings. In Problem Settings, you have Problem Class, Anisotropy Settings, and you require to have this option, General Anisotropy with User-Defined Angles. Okay, so this is mandatory to calculate hydromechanical processes in FEFLOW because the method that we are going to provide requires and computes the anisotropy angles. Next step, we require an elemental selection to be defined for the hydromechanical coupling. Let me change this to element selection, select all the elements, and I will store this selection as rock. I don't need to visualize the selection, so I will just deselect. Now, since I have attached the plugins to the FEM file, I could do right click, edit, and visualize the graphical interface of this plugin. Came some on other screen. Here we will need to create or to do some relations. Total stress is the definition that we already create here. Surface law function ID. This will be the case if we plan to implement overbonding effects in the topography. In our case, we are not going to consider this. No stress porosity could be undefined, is optional. Local deformation is the elemental distribution deformation, and compactation is consolidation. As a next step, I need to create a formation be linked with these hydromechanical processes. I have three possibilities: fractural media, granular media, and faults. If I would like to add a fractural media, granular media faults, I just simply need to press on the corresponding icon. Let me add a fractural media distribution. FEFLOW pops up a dialog which contains the list of selections. I have only one selection in the panel, so I'm able only to select rock. Okay. The name of the selections appear listed in the formations block on the formations list. I could have n number of selections, depends to the different settings that I want to implement. Each selection, each fractural media in this case, requires a parameterization. I could add a number of fracture families. By default, I have one single family, but I could also add different more families. So we can do this. Let's do right click, add family, right click, and add family. The relevant parameters for the calculations are the ones here. Frequency is the frequency distribution of these apertures. If I don't remember the units of these parameters, I can simply click on the parameter and FEFLOW will tell me the meaning of this parameter and the units. This is basically the units, the aperture of the fracture. Poisson ratio relates the stresses, vertical and horizontal stresses. One relevant parameter is also closure stress, which defines the stress in pascals to be used to consider a fracture closure. There is exponential of the empirical model and the distribution of the angles for the anisotropy in each of the families. Okay, so let's start modifying the first parameter, closure stress. So I will modify this parameter with 50 10 to the 6, 50 megapascals. Having smaller values of closure stress means that the material is going to consolidate to be deformed faster. I would like to provide an empirical model with exponent 7, 5, and 5. These models needs to be calibrated and set to a sensitivity analysis study. The direction of the families of the anisotropy is prescribed by the jaw and pitch angle. You can see the information. The jaw angle controls the anisotropy direction in the horizontal plane, and the pitch angles controls in the vertical direction. Let me set this to 0, 0. We will try different configurations, 0, 90 and 90, 90. Another important parameter to modify is the frequency and the aperture. I would say that the aperture here is too big, so let me define the parameter to, sorry, 3 zeros. And this will be even smaller, and this one even also smaller. I would like to put the frequency distribution to half and half. What FEFLOW is going to use in this case calculates the contribution of conductivity for each families and is going to sum up these effects for the entire conductivity. The rest of the parameters, for simplification, I will leave it as they are. Press OK. If everything works, I could just simply leave the dialog without any error message. I would also like to create a definition of the total stresses. For this, I can create the element, a nodal expression, and this expression will be called effective stress. Effective stress are defined as a function of the total stress, so I can do a right click, edit parameter expression, link this expression to the total stresses minus the pore pressure. Pore pressure is a process variable, fluid flow pressure. Okay. I need to be sure that the parameters here are in the same unit. So if the first one is in pascals, then pressure has to be also in pascals. If I double click, I will see here the distribution of the total stresses. Let me go back to the cross-sectional view. In the cross-sectional view, we can define the total stresses here. And I will deactivate the distribution of hydraulic heads. So this is the distribution of total stresses. Now I will go back to the initial 3D model. I would like to set the hydraulic head back to the default 0. So we are going to compute against this and see what is the effect of the hydromechanical process. Okay, we are almost ready to run. Before running the final model, I would like to understand what is the effect of these hydromechanical parameters. Since FEFLOW uses the superimposition concept here, I would like to set the conductivity to 0. And if I set this to 0, the hydromechanical coupling plugin will calculate only the contribution of the mechanical processes. So I will see only this part of the conductivity. Later, understanding these conductivity effects, I could put back the default conductivity, and run it again to see what is the total conductivity and what is the total effect of in the pit dewatering. So let's press start and wait for the results. Yes, let me save the model first. Can demo, save the model, press start, and we will wait for the result. Okay, the calculation is ready. It takes about a minute to solve this problem. If I look at the distribution of conductivity, I see already that the parameters are heterogeneous. Let me look the conductivity in the one direction, 2 and 3. If you remember, we set the initial conductivity to 0. So basically the conductivity that we see here is the effect of the hydromechanical processes and also the effect of the parametrization of the fractional media as a function of the 3 different families. As a test for you, I will leave it increase the aperture by a one order of magnitude and see what is the effect of the conductivity. You will notice obviously there will be an increase of the conductivity in the porous medium. Let's look in the cross-sectional area. This is the cross-sectional plot. If I look the distribution of conductivity, conductivity is also affected by the changes of effective stresses and therefore also by the changes of pore pressure. The vertical conductivity is presented as well here. Let's look the results of the mechanical calculations. We have a calculation of consolidation in meters, and we also have a calculation of deformation in meters. So the area more subject to consolidation and deformation is the area affected by the decrease of the pore pressure in the system. If I would like to calculate the effect of the pit inflow only due to these parameters, I can simply use any panel, the panel ray budget panel, and a selection describing this information. I have already created a selection called pit which contains the boundary condition. I have only in this effect 3 liters per second. Let's see what is going to happen if we put the real conductivity and on top the mechanical processes. For this, I simply need to reload the document and put the conductivity by default, which is 1, and run the problem one more time. Let me switch to the 3D view, display conductivity, 1, create a selection of all the elements, and I can simply do a copy, paste to the 3 conductivities. If the default parameter, default distribution of hydraulic head is 0, save the file, press start, and we will wait for a minute. Okay, the calculation is ready. Let's look the cross section. Let's plot the distribution of hydraulic head. No. Okay, this is the distribution of hydraulic head. Same pattern, inflow left and right, and then low hydraulic head in the middle of the pit. Pressure distribution. Let's look now the conductivity. We have on top the 1 meter per day. We can easily see in the conductivity tree, before was 0.0485, now we have a 1 on top, and the areas not being affected keeps the same default value of 1. If we look the distribution of consolidation, we have a calculation and also the total deformation, the change of porosity. Let's look finally the infiltration through the seepage phase, the infiltration to the mine. For this we open the ray budget panel. I have the selection pits, and now I have 1 liters per second infiltration into the mine. 1,557 liters per second infiltration into the mine. Okay, thank you for participating in this tutorial, and I hope this was of any help for you. Until the next time, have a good day. Bye.